Module 1, page 3, second video. The basic concept of pipeline cathodic protection. I'll be reading my web page during this video, so I'll cut it into little pieces so as not to make it boring. As stated before, everything has a potential which has an effect on its relationship with its environment. Corrosion is affected by this relationship as it is an electrochemical reaction. The basic concept of cathodic protection is that the electrical potential of the subject metal is reduced below its corrosion potential, and that it will be incapable of going into solution or corroding. The reasons for this are given in thermodynamic theory, but these will not be discussed in detail at this stage. Picture shows a CP system current flow causing IR drop as shown as the coloured potential shells due to the resistance of the soil. The corrosion reaction and cathodic protection mechanism has been defined by many scientists and has become established beyond dispute. Many books and papers have been published giving details of the scientific background of corrosion and corrosion control as a result of many years of research by respected and sincere specialists. It is not intended to dispute any of this work or the conclusions drawn. This course is intended to relate corrosion theory to experiences on the ground in the field of cathodic protection and corrosion control. Battery technology can be compared to corrosion control technology. The principles of corrosion reactions are used in the design and construction of expendable and rechargeable batteries and accumulators, which play such a major part in modern life. A battery is designed to allow a chemical reaction to cause an electrical current to pass through a desired path, giving energy to the appliance. The battery has very carefully composed electrolyte which has qualities to ensure a predictable reaction with the other components of the battery. This may seem obvious to the scientists, but it's not obvious to the people who have to apply the science. Corrosion within a battery can be controlled by external techniques which are in common use. Some batteries have a reversible reaction which enables them to be recharged by adjusting the electrical pressure at the terminals of the battery. Many appliances are nowadays controlled by computers to balance the reaction equilibrium to suit their own power needs. This picture shows a lithium battery that powers the BIOS of the computer. It is charged by the power supply under the control of the computer itself. And this is what we are doing when we control corrosion to networks of pipelines. All this is possible in a computer because the battery is a manufactured unit designed for the purpose of receiving and supplying electrical current. Cathodic protection is different. Unfortunately, cathodic protection is not a unit composed of simple elements in the way that batteries are, because the electrolyte is the ground itself. This is an uncontrollable feature with an almost infinite variety of qualities, as seen in the picture of a drawing that I made in the early 1970s whilst I was corrosion control technologist for Shell BP Development Corporation in Nigeria. The picture above is an equivalent circuit diagram of the cathodic protection systems that were preventing corrosion over an area of tens of thousands of square miles and pipelines serving a major oil and gas production company. The chemical composition and electrical conductivity of the ground can span a vast range and can include environments such as seawater, deserts, freshwater swamps, arable and fertilized land, etc., etc. Climatic effects cause variations in the temperature, and depth of cover causes pressure variations which affect the reaction and add yet more indeterminable factors to the reaction. Cathodic protection of such subjects as gathering stations, shown in the picture, at storage tank bases, is relatively simple, but as the size of the structure increases, it extends through electrolytes of different nature, and the reactions at each interface varies. Offshore rigs, for example, have different temperatures and pressures at the seabed to those at the surface, and studies of these conditions have shown that they have substantial influences on corrosion. The indefinable elements in real life. Pipelines are more complex than other structures and can be regarded as many interface reactions connected together in parallel. This picture shows a length of pipeline with 4 coating faults and 2 attachments connected to the earth. The metal element of the reaction can be well defined, and this is specified to a high degree by the designers. The coating metal is carefully designed, the coating material is carefully designed, but it is generally accepted that no coating can be perfect. The faults, that are called holidays, introduce the first indefinable element to the system that requires cathodic protection. During the construction of a pipeline, all possible measures are taken to detect and repair coating faults. So it follows that the location and size of those remaining are unknown and not definable. It is possible to calculate the theoretical resistance of a perfectly coated pipeline, given the specification of the coating and the dimensions of the pipeline. But it is not possible to calculate the resistance of the coating of an actual pipeline. The electrical current measurements taken during routine cathodic protection monitoring show that there is little resistance in the total coating of a pipeline, and this can be explained by the difficulty in quality control during the coating operations and prevention of damage during the construction period. This is almost impossible to control. It is improving, but it is still not perfect, and in my opinion will never be perfect. Also, after the pipeline has been constructed, mechanical damage and other matters can cause coating faults to appear. Perfect coating would prevent any output from the CP system, but undetected coating faults provide paths for cathodic protection current. We therefore know that there are many unspecified metal to electrolyte interfaces present on an average pipeline. The electrical resistance of the pipeline metal itself can be calculated and is found to be very low. The effect that the pipeline resistance has on the complex current paths and variations in potentials is found to be so small that it can almost be ignored. Further complexity, each coating fault is a metal to electrolyte interface which is capable of a different reaction, electromotive force, which cannot be measured as it is in parallel with all the electromotive forces on the same section of pipeline. If you can have a look at this very simple drawing of 6 batteries and a voltmeter and a ground contact electrode, you will see that the batteries, which I've shown to be half buried but all connected, and the problem is to define the voltage of each battery. It's impossible. The magnitude of the current from each of these is dependent on the earth resistance immediately adjacent to the interface with the battery, and the current directions is a result of the combined effects of all the resistances and electrical pressures caused by the other electromotive forces. Although it is simple to understand each corrosion cell and the mechanism of corrosion itself, the reality of applying the science in the field becomes immensely complex. This becomes more obvious when the circuit has been subject to complex modelling, to computer modelling, as discussed later. To be effective, cathodic protection must reduce the metal potential at each single interface to below its corrosion potential. This is not too difficult to achieve, as each interface is part of the same structure which has a very low electrical resistance. The difficulty is knowing when all the interfaces have been reduced to below their corrosion potential in relation to the electrolyte in their reaction vicinity. Now, I have modelled this situation using batteries, and I have connected a recording voltmeter which can be converted into a data logger, and if you bear with me you will see that this can show when it reacts. This is a bit of software that makes this instrument into a data logger, and when I connect this up, this button, and push this button, hopefully, there you are. So this instrument, this instrumentation is similar to what we use in the field, and what it does is it records voltage readings. As the voltage change, it gives a graphic display. So I will disconnect the battery and reconnect the battery, and you will see that it is actually recording the voltages as we go along, and these recorded voltages can be made into a graph. Now, this is one single battery, so this is a single circuit, a single corrosion cell. But what we need to know is when there are more than one corrosion cells on the circuit. So now we have a situation where we are showing minus 2.783 volts, and we switch it off and we switch it back on, and we see that we have a graph of both corrosion cells in series on this recording voltmeter. We need to know the strength or the potential or the EMF of each of these corrosion cells, and we cannot know it through this recording. It gets worse, because if we add yet another corrosion cell to the recording, we get a different reading. Now, this reading is different from this reading, and it's different from this reading. It all depends how I arrange the corrosion cells that we are measuring. On a pipeline, we cannot arrange the corrosion cells. They are just corrosion cells on a pipeline. And that's the reason why I have made this model, because it shows the impossibility of interpreting pipe to soil potentials. We cannot interpret or analyse the graphs that are produced by close interval potential surveys or direct current voltage gradient surveys. They cannot be analysed, and no meter in the world can possibly measure the correct measurement that we need to analyse corrosion surveys as they are at the present. That is the reason why I devised the Alexander cell, which is in fact a corrosion cell that we can measure the corrosion current, and we can measure the potential at the anodic interface with the environment.